Hello all, just wanted to give a little bit more information regarding specific heat and give you guys another example as we start to work these calculations. A lot of different ways we can start to work these, and I just want to make sure you guys are feeling comfortable as we continue to move forward. I felt like we ran just a little shy on time as we were talking about this. Just a little bit more on specific heat. We talked about heat capacity, and really what that is describing is how well our substance is absorbing that internal heat energy. And so by definition, it's the amount of heat energy needed to take 1 gram of a substance, whether it's a metal or a liquid, water, alcohol, ester, whatever it might be, and to take that gram of a substance and change its temperature by 1 degree Celsius or 1 degree Kelvin, 1 Kelvin, excuse me. Units then are going to be joules per gram Kelvin or joules per gram Celsius. And this is just dependent on how you measured that change in temperature. It is an intensive property. That means it does not depend on the sample size. Whether you are talking about 50 grams of copper or 100 grams of copper, how well that copper absorbs that heat energy is going to be the same. It might just take more energy to change all of the copper to a new final temperature. But how well it absorbs that heat, its specific heat capacity is irregardless of the amount of the substance. It's intensive property is what that means. But oftentimes, when we're looking at our systems, our chemical reactions, we are working with aqueous solutions. And so we got to be a little different when we start to look at our reactions. Sometimes we're using solid, which is great, yay, mass, but aqueous solutions get a little trickier. I want to give you another example of this as you start to kind of navigate these calculations. So let's say you place 50 milliliters of a 0.5 molar sodium hydroxide solution, the calorimeter at 25 degrees Celsius, and added an additional 25 milliliters of a 0.5 molar hydrochloric acid solution, also 25 degrees Celsius. After stirring, we measure the temperature and find that the final temperature is 21.21 degrees Celsius. And so we can, in fact, actually, based upon the change in temperature and everything happening kind of in our solution, we can figure out how much our heat energy has been either released or gained based upon our final results. Now let's think about this. We went from 25 degrees to 27 degrees. That would indicate to us that this is an exothermic reaction. It is releasing heat energy, and for that we would then expect that our delta H would be a negative value, right? Okay, good. First, we got to start by finding Q. Well, we know that to find Q, it's going to be Q equals MC delta T. Well, what is M? We're adding sodium hydroxide, a strong base, to hydrochloric acid, which is a strong acid. This is a neutralization reaction. We're going to make water. And the good news is we actually know the total volume of the water. We added 50 mils to 25 mils. That's 75 mils total. And the density of water is 1 gram per milliliter. So if we have 75 milliliters, this final mass of our aqueous solution altogether is 75 grams. And we made water. It's the reaction taking place. Technically, we're making sodium chloride, but that sodium is still floating in solution, as is the chloride. Those are both aqueous salts. And so they're not reforming any bonds, releasing any heat energy. The heat energy produced here is coming from the water. And so we now know how much water we've got. It is our 75 grams of water. And for water, specific heat for water is 4.18. We know our C. But we're in our Kelvin units here. I think our temperatures here were provided in Celsius. So we would add 273 to both of these. We would then subtract them to get the difference, and we would get our values for Q equals MC delta T. Here's our 75 grams of water, specific heat of water. Here's the difference in temperature, but it's in Celsius. Oh no. We do. But if you add 273 to both of these and then subtract them, they cancel out. Oh, that's pretty slick. We can multiply all those together. Our degrees Celsius here cancel, our grams cancel, and we then get into our joules of energy. Cool. Now, oftentimes when we're doing delta H, we use kilojoules, specifically kilojoules per mole, because we want for a balanced reaction, for our reactions we saw before, we know that we want our kilojoules per mole. And so we would need to do a little work here. We need to figure out how many moles of hydrochloric acid were in solution. Oh, that's not too bad. All right, I think we have both the molarity and the volume of that hydrochloric acid. We can multiply those together to find the moles of our acid. And so now if we know how many joules of energy were released, and we know the moles of acid we used to form that energy, we can in fact solve for how much energy per mole. Now, technically, this should have a negative on it. This is an exothermic reaction. It would be negative 55.4 kilojoules per mole of hydrochloric acid that is leaving our system, being created or released in the form of temperature. Cool. Just want to give you another example of this, so that as you're working these calculations, you've got one to come back and reference. Again, feel free to see Mr. McDonald if you've got any questions. I know he'll be popping in and out over the course of the week. Best of luck, and feel free to email me as well if it is something that's really giving you a hard time. Thanks, and best of luck.